Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. As part of my gigacasting series, I hinted to the fact that magnesium castings would weigh 33% less than aluminum castings, and that magnesium is the lightest structural metal. If that's the case, why aren't companies like Tesla using magnesium gigacasting for vehicles instead of aluminum castings? In short, it's because magnesium components historically faced a number of engineering challenges. In today's video, we'll look at how each of those challenges have been addressed in the last couple of decades, or will be addressed in the next few years by some of the biggest players in the industry, like EDRA. As with the gigacasting series, this video kicks off a new series on magnesium, and it'll be followed by at least 3 other videos that explore the engineering solutions covered briefly today in much greater technical depth, along with their implications. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. Flammability is the first challenge for magnesium. Pure magnesium readily ignites at around 500 degrees Celsius, and that's often cited as a reason why large magnesium castings aren't viable for vehicles. But that thinking is reductionist, and there's a lot more to the story. Let's start with the worst-case scenario. Pure magnesium. Most people's first experience with magnesium was from high school science class, where the teacher might burn a strip of magnesium to show off its brilliant white flame. However, when magnesium is used in products, you're looking at a much larger piece of magnesium, and it's almost never pure magnesium. As for the former, a larger piece of magnesium takes much more energy to heat, and magnesium also has high thermal conductivity, which allows it to dissipate heat rapidly. Thanks to this clip by Magrathea for today's video, we can see that it takes minutes or longer rather than seconds to ignite an ingot of magnesium. What's happening here is that the magnesium ingot is absorbing a lot of energy and it's heating up, but the energy input from the flame is being balanced by heat conduction away from the flame. That heat dissipation effect is so strong that with the amount of heat being applied here, the ingot may actually never ignite. What this means is that even if pure magnesium was used in a vehicle, it wouldn't be a risk for triggering vehicle fires, and it's far safer than substances that are already used in vehicles like oil or gasoline that are triggers for vehicle fires. Note that I said to trigger the vehicle fire. Extinguishing a vehicle fire is another story. More on that in a moment. As a side note, one thing that's often missed when discussing the flammability of magnesium is that other metals such as iron and aluminum can also ignite in the right conditions, such as when they're in powder form, molten, or exposed to oxygen. So although magnesium is more flammable than iron and aluminum, the fact that it is flammable doesn't make it unique among structural metals. It's just that the risk of flammability is higher. But again, it's far less flammable than most of the other materials used in a vehicle. Now that we've looked at pure magnesium, let's take a look at the impact of alloys on flammability. The magnesium alloys commonly used in consumer products have a better balance of properties than pure metal. One of those properties is fire resistance. Alloys starting with the codes AZ, AM, AS, and AE are commonly used in automotive parts. They have ignition temperatures that are about 50 to 100 degrees Celsius higher than pure magnesium, and as we'll see in a moment, they burn less intensely. More recent advances in fire-resistant alloys from the Austrian Institute of Technology, or AIT, show that the addition of calcium and yttrium allow magnesium to be heated to its molten state and it doesn't ignite. That was confirmed in testing by the Federal Aviation Administration, and the alloy has been approved for use in jets. It's not clear how much calcium and yttrium AIT used to achieve that result, but their patent application indicates that it's likely between 0 to 1% calcium and 0.05 to 0.6% yttrium, so the dopants only made up a fraction of the alloy. Let's look at a video of how it performs versus more common alloys. On screen is a video from AIT comparing magnesium alloys such as AZ91 and AM60 with the calcium and yttrium alloy. Bear in mind that they've used small pieces of magnesium for demonstration purposes to accelerate the speed that melting and ignition occur. After about 1.5 minutes, they both melt. However, whereas the AZ91 and AM60 alloy goes into thermal runaway and slowly catches on fire, the AIT alloy remains in its molten state and doesn't catch on fire. This shows that common alloys have better thermal performance when exposed to flame than pure magnesium, but calcium and yttrium can be used if more robust fireproofing is needed. That might be useful in the future when more magnesium is used in vehicles. That's because magnesium fires react violently to water, and the amount of magnesium that's already used for vehicles is a safety concern for firefighters. With that said, the challenge with magnesium fires needs to be put in perspective. Firefighters are familiar with putting out magnesium fires in vehicles because it's been used by the automotive industry for about 100 years already. That's as opposed to battery fires, which arguably pose a greater challenge for firefighters. Why? First, because battery fires are self-sustaining electrochemical fires that can reignite weeks after the fire is presumed to be out. Second, because there's usually about 1/4 ton of battery cells in an EV that are encased in a metallic enclosure deep in the core of the vehicle, which means they can be difficult to access and extinguish and can take days to cool off. Third, because they generate toxic fumes such as hydrogen fluoride. That's as opposed to magnesium, which reacts with oxygen to form magnesium oxide, which the body can process. So the main concern would be all the other materials burning in the vehicle fire, like paint, plastic, and other metals like aluminum. Fire departments are adapting by using fire blankets to help control and extinguish fires and burying the cars in sand for a week to prevent reignition risks. Interestingly, the same or similar strategies used for battery fires will also work on magnesium fires, but that's a topic for another video. Overall, the key message here is that magnesium won't trigger a vehicle fire. And although a vehicle fire that involves magnesium is more difficult to put out than a regular vehicle fire, it may actually be a smaller concern for firefighters than the battery pack of the vehicle. That is, the flammability of magnesium is commonly put forward as the reason why it isn't used more heavily in vehicles. But that's not the technical reality. Let's move on to the next challenge with magnesium, which is that it's highly susceptible to corrosion from chemicals like sodium chloride. Once again, while corrosion makes pure magnesium fundamentally unviable, with the right alloys and surface treatments, magnesium fares well against corrosion, and there's a lot of work being done to improve that even further. For example, in 2021, researchers from the Helmholtz Center for Materials and Coastal Research in Gstaad reported a new magnesium alloy that's so corrosion resistant that they called it stainless magnesium. On screen are some of the images from that research where 3 alloys were exposed to extreme corrosion conditions. On the far right is a common AZ91 magnesium alloy, which in newer blends tends to have good corrosion resistance similar to aluminum. And the center is an E21 magnesium alloy with great corrosion resistance. And on the far left is a new alloy using only 0.15% calcium that has excellent corrosion resistance. After 6 months in a solution of 3.5% sodium chloride, the AZ91 is fully degraded. The E21 is showing pitting and surface corrosion, and the new 0.15% calcium alloy is just starting to show some surface corrosion. How does that work? The researchers claim that for the stainless magnesium, the calcium creates a protective surface film and stabilizes impurities within the alloy to reduce the corrosive effects of the sodium chloride solution. And because the calcium is used in such small amounts, it's able to do that while maintaining the properties of pure magnesium. That is, just like we saw with flammability, there's alloys available to mitigate the corrosion challenges with magnesium. It's also worth noting that besides corrosion-resistant alloys, magnesium parts can also be coated in a number of ways to further increase corrosion resistance. So if there is a use case that requires even better performance, there are solutions available. Before we move on, it's worth making 2 more notes on alloys. First, over the past several decades, dozens of magnesium alloys have been developed that offer not just corrosion and fire resistance, but also a range of strength and ductility characteristics. Thanks to that, magnesium is already being used for or considered for use in a number of automotive components. That is, for the most part, the range of performance characteristics offered by magnesium alloys already make magnesium the preferred metal for a number of use cases. So what's actually holding magnesium back? We'll take a look at that in a moment. As a side note, I'm focused on automotive use cases today, and that'll continue throughout the series because that's where I see the biggest and most exciting opportunities for magnesium in the coming years. The second note on alloys is that even if there is a use case that magnesium alloys haven't been developed for yet, more alloys can always be developed. As I showed in my gigacasting alloy video, Tesla's gigacasting process was a new use case with new requirements, so they developed a new alloy. The link for that video is in the card above. Next, let's move on to size limits. In the past, it was possible to make large magnesium castings, to make magnesium castings at a high production rate, and to make ultra-high quality magnesium castings, but not all three at the same time. For example, typical molten metal and cold chamber die casting can create large castings at a fast rate, but those parts tend to have high porosity. That is, they're lower quality than what other methods can produce. But the magnesium casting industry is about to change. Idra, which was the first supplier for Tesla's gigacasting machines, recently gave a talk where they shared a roadmap for 2025 for magnesium chip casting, where they indicate that they intend to produce what they refer to as gigaplast machines that can support shot weights for magnesium castings of up to 20 kilograms. The best information I can find indicates that these types of machines were previously limited to shot weights of around 10 kilograms, but even that is a recent development from earlier this year, and most machines up until a few years ago were limited to less than 5 kilograms. The question is, are the gigaplast machines able to produce those large castings at high speed and ultra-high quality? In short, yes. First, with regards to production rate, magnesium has a lower heat of fusion and it's less dense than aluminum, which means for the same amount of cooling power and volume of material, magnesium solidifies more quickly. Additionally, molten magnesium is less reactive with the die, or metal mold of the gigacasting machine, which means that cast magnesium parts aren't as prone to sticking to the die and can be removed easily. That's as opposed to aluminum, which does tend to chemically attack and stick to the die, making it more difficult to remove the castings. The combination of those two things means that the cycle time for magnesium castings tends to be faster than for aluminum castings. So at a first principles level, speed won't be an issue for Idra's magnesium chip casting machines. Second, what about quality? The chip casting that Idra refers to is a thixomolding process, where magnesium chips are fed into an auger. The auger is surrounded by heating elements that warm the chips until they're semi-solid, like the consistency of soft butter, before being injected into the die chamber. That butter-like consistency means that when it's injected into the die chamber, there's no turbulence like there is with the fully molten metal used for aluminum casting, which means fewer voids in the material, which in turn means higher part quality and consistency. Why does that matter? As Sandy Monroe said in a recent video, thixo-molded parts bring the performance of cast parts closer to the performance of a forged part, which means lighter and stronger parts. That, in turn, means magnesium will become much more competitive with cast aluminum parts as a structural component within the vehicle. Thixo-molded magnesium may even open the door to massive magnesium underbody castings that may replace their aluminum counterparts, which could remove tens of kilograms of mass from vehicles while creating a better overall driving experience. I'll get deeper into that in the next video. Next, availability and cost are closely related, so I'll cover them at the same time. I'll start with availability because it drives cost. This image shows that roughly 950,000 tons of magnesium were produced in 2021, which is small compared to its closest functional competitor, aluminum, which saw 68 million tons of production in 2021. Why is magnesium produced in such low volumes? Is there a resource constraint here? The answer is no. Like aluminum, magnesium is an abundant rock-forming element. In fact, when I looked up the U.S. Geological Survey data on magnesium, it's so plentiful that they don't even bother listing reserves, but rather just say that the reserves are sufficient for any potential future needs. If it's not a resource issue, is it an extraction issue? At a fundamental level, no. There have been ways to extract magnesium since the 1800s, but it wasn't until World War I that high-productivity, modern processes began being developed, and it wasn't until World War II that a forcing function was created to scale production. That should give a hint as to why magnesium is produced in such low volumes. Its closest competitor, aluminum, had a head start. In the late 1880s, the modern process for producing aluminum, the Baer process, was invented. So depending on how you look at it, aluminum was able to start building significant industrial scale 20 to 50 years earlier than magnesium. That means aluminum production and the development of aluminum alloys had a lot more investment dumped into them at an earlier date, which meant larger scale, lower costs, and better performance at earlier points in time. That created a competitive headwind for magnesium. With that in mind, it's clear why the magnesium market is 1/60th the size of the aluminum market. Moving along, the small scale of the magnesium market means it's much more expensive than it should be, and also means there's not much depth to the market, which in turn means supply and price instability. That makes magnesium a hard sell because it's cheaper and less risky for companies to just use aluminum. However, I expect that to change as both the cost and benefit sides of the equation improve for magnesium. As I pointed out earlier in the video, the benefit side of the equation is improving as magnesium's drawbacks have been and are being addressed through chemistry and engineering. That means independent of any other variables, the demand for magnesium will be increasing because it will be increasingly viable for more use cases. While we're on the topic of demand, in addition to the chemistry and engineering improvements, there's another tailwind for magnesium that'll mean increasing demand for the metal as the decade progresses. Electric vehicles. Using some very rough back-of-the-napkin math, for every 2.2 kilograms of weight that can be removed from an electric vehicle, about one 4680 sized battery cell plus the packaging material around that battery cell can be removed from the vehicle. Each of those cells probably costs about $10 with packaging, and that's just for the battery. The lighter battery pack would in turn also save money in the suspension, motor and inverter power, brakes, and the structural reinforcement needed to carry the battery weight. That means even with a slight cost premium at the material level, magnesium can reduce the total vehicle cost. So even if there were no advancements in magnesium alloys or manufacturing processes for the rest of the decade, we're still going to see the demand for magnesium increase because the economics of EVs are creating a forcing function for lighter materials, even if those materials are more expensive. That increased demand will drive investment, which will drive innovation, development, and scaling, which in turn will increase supply, which brings us to the cost side of the cost-benefit equation. We're already seeing companies poised to tackle the supply, price, and price stability challenge from companies like Magrathea. Not only that, Magrathea in particular is working on a process that'll produce magnesium with an unparalleled environmental profile compared to any other structural metal. That leads us to the final challenge with magnesium. In terms of production, in the past few decades, it's had a poor environmental profile. That's because magnesium has mostly been produced in China since the 1990s using environmentally disruptive processes that are primarily fed by coal power. Magrathea is working on a process to extract magnesium from seawater. If that sounds far-fetched, first, bear in mind that seawater contains about 1 pound of magnesium per 142 gallons, or 1.85 kilograms per 1 cubic meter. Second, as I showed on screen earlier, Dow Chemical started extracting magnesium from seawater in the 30s and 40s, and they continued to do that profitably until the 1990s when China entered the market. That is, we're not talking science fiction here, but rather resurrecting and improving an old technology that wasn't just profitable for Dow, but also Norsk Hydro, What this means is that even if the metal that Magrathea produces is a similar cost to the rest of the magnesium on the market, it'll still be much more desirable than the magnesium produced in China because one of the primary metrics for EV makers is lifetime CO2 emissions. But if Magrathea can not only reach cost parity with conventionally produced magnesium, but produce it more cheaply, which is their goal, they could see huge demand, and they quite literally have an ocean of material to tap into for effectively unlimited scaling. In summary, in the past, there have been legitimate challenges that stood in the way of magnesium becoming a material that's embraced by the automotive industry, and many other industries for that matter. The flammability of magnesium is, or was, a challenge, but the attention it still receives is disproportionate. Magnesium, and especially its alloys, are less flammable than most materials in a vehicle, particularly fuel and batteries, and there are even aircraft-grade alloys that don't ignite. Corrosion was already solved for many use cases, but now there's stainless magnesium for extreme use cases. As for size limits, with IDRA's new Gigaplast machines, the industry is moving towards large castings that can be produced at a high rate, but should also be high quality, meaning low porosity cast parts that are stronger and behave more like forged parts. Availability and cost are being tackled by Magrathea, which is tapping into an ocean of supply while at the same time producing magnesium that, unlike the magnesium produced in China, will be inherently carbon neutral. With that in mind, my view is that we're going to see an S-curve over the next 5 to 10 years where magnesium starts to displace aluminum as the dominant structural metal for lightweighting and simplifying vehicles and other mass-sensitive applications. In the next video of the magnesium series, I'll walk you through IDRA's plans for thixo-molded magnesium, and after that we'll look at Magrathea's plans to resurrect the extraction of magnesium from seawater. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers, like my Patreon supporters, generally get access to my videos a week early. On that note, a special thanks to my YouTube members, X subscribers, and all the patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.